Alright, so I wanted to sort of discuss this example where there's a block sliding down a frictionless surface, and it would be speeding up, right? So the velocity would be increasing. There's a motion map for it. Drawing a force diagram, right? We'd be looking at weight flowing down, normal, kind of at an angle, right? And I'm assuming it's frictionless. So that's it. And when I do a vector sum diagram, maybe I would do the normal and then the weight, about like that. Weight I'm going to replace with mg, normal like that. And our net force, which is our ma vector, would have to be pacing down the hill in the same direction as our acceleration, right? Because ma is a vector it has a in it. Ma is a vector that's in the same direction of the acceleration, but it's multiplied by a scalar m, which the scalar just changes the length of the vector. Okay? Anyway, I'll do some reference lines now. There's some reference lines. Here's a couple more. And typically in a problem like this, you might know what this angle here is, which in my force diagram would be right here, right? Which is right here, which is right here, which is right here, right? So on my vector sum diagram, that would be this angle right there, right? So now if I do sine of that angle theta, I get ma over mg. Notice this is a right triangle right there, which means sine theta is going to equal a over g, which means the acceleration of our block has a magnitude of g sine theta. Okay, so that's the acceleration of our block. Now we could sketch a stack of graphs, right? A versus t. I'll make down the hill positive. Okay, so our acceleration therefore would be positive. Okay. Whoops, I didn't want to do that. Anyway, so as I said, the acceleration down the hill would be positive, right? And I was drawing sketch a graph, right? So acceleration, which is positive, would be, oh, that's kind of cool. There we go. So acceleration, which would be positive, would be kind of a shape like that, right? And velocity, let's say our block started from rest to make things easier. Okay, so I'll write v naught equals 0. And that means that our velocity graph might look something like that. Okay, and our acceleration is g sine theta, right? So this area, therefore, would be our change in velocity, which would be, let's see, g times t sine theta, right? So the height of this graph, this triangle, at time t, right, the displacement, right, this is our change in velocity, so our displacement would be gt squared sine theta, right? And yeah, I think that's pretty cool. So maybe I did something wrong. Hold on a second. Yeah, this is I need to divide by 2 because that area is a triangle. There we go. I think that's right now. And you'll notice that that is exactly the same thing as delta x equals 1/2 at squared, right? Because g sine theta is, let's see, I'll rearrange this, make it look better. This is 1/2 g sine theta t squared, right? That's the same thing. So that's simply 1/2 at squared. Anyway, hope that helps, and this is just a sort of basic Newton's second law type problem. One other thing you might want to do is check out cosine theta, see what that can show you. You can probably find the magnitude of a normal force, right? So cosine is normal over mg, so your normal force is going to be normal equals mg cosine theta. And notice that normal force depends on the mass of the object, but your acceleration will not. Anyway, have a good day and take care.